Hello everyone, I'm Harish Sitaraman. I'd like to start by thanking the NANOG program committee for accepting our talk, and I'd like to do a shout out to my co-authors of this presentation, Pavan and Mazen. So I'm going to be talking about RSVP Pop&Go today, just give you a feel for what it is. It's something new that we've been working on, going through the ITF. So I'm going to start off with motivation, generally give you a picture of why we're doing this. Just a quick slide of just all the feature sets that RSVP has been providing in all these years. What does it mean to take RSVP and couple it with a shared forwarding plane when you start sharing labels in the middle of the network? We'll get into the details, show you some couple of show outputs, and we'll wrap up. So we start off just by looking at what it means to do TE, what is the infrastructure that one needs to do traffic engineering in a SR deployment, right? So at first you need a controller. Some form of a controller is necessary to handle bandwidth usage of the network, right? So you could either go build your own controller, various options. You could go buy a controller from different vendors, and you have to come up with your own deployment model. So cluster of controllers, availability, all that stuff. The controller actually has to learn the topology. So there are various ways to learn the topology of the network. BGPLS, PSEP, LSDP streaming, you pick your favorite option. And then you will also have to learn the various events and capabilities that are going in the network. And then the controller has to do a path computation, right? So there are operators who want to write their own path compute algorithms, and once you compute the path, you have to go and program it back into the edge devices so that you can actually steer traffic into the network. So you could use again PSEP, BGP-SRT, static segment routing T, programmable APIs, various again different options. With respect to telemetry, the controller, now that it's placed all these paths, has to listen to feedback loops from the network. It has to listen to telemetry because you don't know where the traffic is. You don't know which links are getting congested. The controller thought that this is the best path, and it has to listen for statistics data from the network to understand. In order to even do like optimizations, for example, path optimizations, all of that, it needs the data back from the network. And at any point, it's good to know where your traffic is. So since there isn't a clear concept of, we share labels across the middle of the network, it's the idea of a label belonging to a particular path goes away. There are other considerations that the controller has to consider. One is the label stack push step. So if you want to push a stack of labels, the controller has to know how many labels the box can push. That's a very vital piece of information. The second thing is once the controller figures that out, there is an implicit assumption and belief, right? But aggregated interfaces are being deployed everywhere. The routers have to do good hashing in order to pick a good member link. And this is fundamental, right? So all different chipsets have, different vendors have different capabilities of how many labels it can actually read in the stack and be able to get to the IP source and test. And that's also a very important piece of information for the controller to know, because you can go push 20 labels on a node, and the next hop may just not be able to parse through all that and be able to get IP in order to get a good hash. Right? So the controller has to know that. There are obviously solutions that have been proposed to go and solve that using entropy labels. Here you can insert 2 labels or more, multiples of 2 in the stack to create better hashing, but then you are actually taking space away from what is already a very precious resource, which is your label stack. The MTUs have to be adjusted across the network to handle the overhead of the number of labels. So all of these are just considerations. There are drafts available for all of these flooding, push depths, receive label depths, all of that. But the controller has to sort of understand this to generate a good path. As also there is the thing where loose hop routing and ECMP, right? So with, in general, if you look at TE, traffic engineering is generally a strategic idea. So in general, people have been strictly routing TE through paths, right? With loose hop routing, there is this concept where, okay, let's take the shortest path to a given destination. And in reality, you don't know where your traffic really is. So there are proposals where, you could put like multiple stacks, multiple labels, and you roughly know where the traffic is. So I think so some of that, at least with traditional TE, strict hop routing provides you the ability to know exactly where the traffic is. And all of this infrastructure has to work in a multi-vendor network. Now, this isn't to say that, all of this is just to give you a reference of the infrastructure one has to be committed to build or deploy, right, in order to make TE work. So we're just going to do a quick snapshot of what RSVP has been providing in all these years. Distributed path computation, and signaling with bandwidth admission control. A lot of customers in backbone networks, especially in the US, across the cloud vertical, across service provider backbones, use bandwidth admission control. So in RSVP, a fast reroute has been provided. Auto bandwidth is used a lot. So you don't have to pre-provision for bandwidth in the network. You can just create the LSP, let the traffic flow, and then you can decide. And then the LSPs automatically adjust their bandwidth based on the traffic. Offers LSP priorities, preemption, high priority, low priority. And off late, we've seen increase in deployment of technologies like TE++ and containers, which allow you to do better bin packing in the network, which also allow you, so there are many deployments which do multiple LSBs between a source dust pair. So instead of statically going and provision them, technologies like these allow you to just create the optimum number of LSPs as needed by the traffic at that point in time. It's an automation framework. And of course, with multicast, it offers you a common MPLS data plane for unicast and multicast. So let's look at the states, right? So RSVP is, always people talk about state. So there's control plane state, obviously. It's a signaling protocol. It goes along, creates state on every node. It does bandwidth admission control fundamentally with that. There's a lot of scaling work that's happened in the IETF. I think this draft that's on the slide is just about to become an RFC. There's a lot of recommendations. This summarizes all the scaling extensions or just efficiency extensions. We send like soft state messages in RSVP. Now the draft proposes, you don't have to send it all the time, send it every 20 minutes or so. So you don't have to be very chatty, right? So it does a lot of improvements in the signaling aspect. And then if you look at the forwarding plane state, it's always directly proportional, right? So if you have 10,000 transit LSPs, you actually have 10,000 labels in the data plane. So there's a one-to-one directly proportional. And transit data plane churn. So when customers run like auto bandwidth, LSPs continue to keep doing make before break all the time. They keep moving. So as they keep moving, they create new label states, and then the old LSPs need to get deleted. So routers are constantly trying to allocate labels, program the fib, send path messages up, and then delete the old state. And there have also been situations where, like, chipsets have had limited capabilities of how many labels they can actually support in the LFIB. We've seen cases where we have had to restrict the number of labels the box can actually allocate, which in turn restricts how much the signaling plane can actually scale. So what does it mean to take, like, say, we decided, okay, well, we take RSVP, and we take some abilities, so what it means to do a shared MPLS forwarding plane. What if you start sharing labels in the forwarding plane? What benefits do you actually get? So the URL there is to a draft that was accepted by the MPLS working group. It's a multi-vendor and operator supported draft. And so the what if you could reduce transit data plane state at an LSR, right? What if you could share all these labels across various numbers of LSPs, regardless of where the LSP is starting from and where it's going? What if you don't have to program your fib anymore? And we actually have it's a self-contained solution where it actually overcomes label stack push dip limitations on the box. So if a box can only push 5 labels, that's great. That's all you can do. We'll work with that. right? And you can continue to use all the RSVP TE features, FRR, and all the feature sets that we talked about in the earlier slide. So with respect to where it's positioned, right, it's just another data plane. It's another tool in the toolkit in TE. It's another data plane. There are customers who are happy with backbones having certain RSVP, the volume of state it has, it has a lot of fib state, but it also offers you a very fine statistics granularity. So one can actually go to a transit box, look at a label and say that belongs to this LSP, and I want to see how much packets are on that LSP, right? So it allows you that statistics granularity should you need it. On the other spectrum is the forwarding data plane that we're talking about now, which looks like an SR MPLS data plane where you have least fib state, but at the expense of maybe you don't have that fine granularity of LSP stats because you are now sharing labels across LSPs. So it's not like one is better than the other. It's just a choice of what you have. So we'll get into a little bit of the details now in the next few slides. So we introduce this TE link labels, right? So for each TE link on a router, you allocate a label, and you install the label in the LFIB, and you basically set it to a pop and forward label action. So the example there shows like if you get a packet with label 1000, the router will basically pop the label and push it down the interface, G001. And if it gets a packet with label 1001, it'll pop that and send it across that associated interface, right? We have about maximum 2 labels per interface because RSVP has the concept where some LSPs can be protected and some LSPs doesn't have to be protected. So you actually need 2 labels, one to cater to having a bypass next hop or protection, another label which offers no protection, right? So different LSPs can actually pick different labels. So about 2 labels per interface, and the scale is roughly approximately the number of neighbors that you have on that box. So if you look at the LFIB, that's about the number of labels one should see with TE link labels. All right. So how do we start sharing labels between LSPs? So the diagram actually shows a green LSP at the top and a sort of a blue LSP at the bottom. We introduce the concept of label stacking in RSVP. So typically in RSVP, the ingress pushes one label and the transit swap labels. So here the ingress actually is going to push a stack of labels. And the stack, if you look at it, the green LSP at the top, so it has a stack 200, 300, 400, packet coming at 200 to R3, it's actually popped, pushed down to R4, get 300 pop, pushed down to R5, popped and pushed down to R6. So in this example, right, the red links in the middle are actually shared by both the LSPs. And actually, if you look at the label stacks, both of them have 200 and 300 at the first 2 labels at the top. All other things that you're familiar with, like bandwidth admission control across a TE link, all of that just works unchanged. So even statistics gathering for auto bandwidth, for example, you could have 10 green LSPs at the top. They all have the same stack, but you can account for all of them statistics independently, just like it's done today. For example, a good analogy from today is one-hop LSPs. So if you have one-hop LSPs, there's no labels on them, you could have 10 of them going to the same router, you can still account for stats on all of them, and you could do auto bandwidth or various other things on it, right? So where do these labels come from? From RSVP signals the path message. We get a record route object in RSVP, it's always there. It actually records all the labels and the addresses. So the ingress actually just parses the record route object and then creates the label stack. So now the next question obviously is, we have introduced label stacking on RSVP, and you just talked about limitations of number of labels that a box can push. What's the catch? So we have this automated way of delegating a label stack push. So let me just work around some assumptions, right? So let's take this, let's walk with a few assumptions here. Let's assume every box in this network can only push 5 labels. And every box in this network can only read up to 8 labels, such that it can also get to IP header for hashing. Let's say if you send it more labels than 8, let's say it can't get to the IP, right? And the ingress, let's say it's running a bunch of services, it needs 2 labels for services, maybe L3 VPN, whatever, so you need 2 labels there. So the ingress in net effect can actually only use 3 labels for RSVP, right? So it pushes 3 labels, and the 3 labels get you the packet all the way up to R4. And in R4, in turn helps, it's called a delegation hop, it's a delegation helper. So he delegates, he has a delegation label there called 350. This is slightly different from the TE link label, right? So R4 actually allocates this label specifically to impose a label stack. Now this delegation label can actually be shared across various LSPs, and it imposes the rest of the labels down the stack, which gets the packet all the way to R10, and then he in turn pushes the rest of the stack to get the packet to the egress. This is completely automated. The network does the best it can given its capabilities. A box sort of needs to know only its own ability to push labels and its own ability to read number of labels, right? We'll get to how this works in a slide from now. So the attempt here is to never send a packet to a box that it can't really read. Never send more labels to a box that it can actually read and be able to get to IP. All right? So that you don't have to try to burn more slots off the stack using entropy labels or any such mechanisms. You just don't send packets to a box more than what it can actually read and use for hashing, such that you can get to IP source and test. Right? So if you look at this, basically we have the red labels at the bottom of the stack. They're actually the delegation labels. So if you look at R4, that's a 950 at the bottom of the stack. It gets the packet to R9, right? So the idea is every stack here gets the packet only to the next delegation hop. So I'm interested in only getting the packet to the next delegation hop. He gets it to the next delegation hop, and eventually we get to the egress. This concept is important. So I'll illustrate another thing in a slide from now. And there are two different forms of delegation that we have. One is automatic delegation, and the other one is explicit delegation. With automatic delegation, the concept is the network does the best it can. You have the boxes that you have, the hardware does what it does, and so we work with that. So as long as that box knows what its capability is, as long as that box knows it can push only so many labels, receive only so many labels, that's all it needs to know. And we do the best we can with that ability, right? So ingress in this scenario, an automatic delegation doesn't need to be aware, nor does any box in this network need to be aware of anybody else's capability. The network uses what is called an ETLD field. It is introduced in RSVP. It's a 32-bit field that gets signaled in the RRO, and that's how, in the next slide, we'll explain how that actually works. Or we have explicit delegation. You could put a controller in the network. You could use PSEP or anything to actually control the RSVP LSP. And if the controller has all the information regarding the network, it can actually dictate and tell the network to dictate who should be the delegation hops, for example. So this slide has the magic on how the automatic delegation actually works. So this ETLD field goes in the path RRO in RSVP, in the path message, right? So if you look at R1, he sets an ETLD of 3. What he's trying to say there is, I can potentially send you 3 labels in the label stack, in RSVP level, right? And the ETLD field gets decremented at every hop. It doesn't exactly get decremented. Every hop decrements and adds a new ETLD field in RRO, but for the sake of simplicity, just say it's decremented. When the ETLD field reaches R4, it becomes 0. So R4 says, I'm going to automatically select myself to be a delegation hub. And then he resets the ETLD to 5 because he says, I can potentially send 5 labels now on the stack. I can push up to 5 labels on the stack. So I'm going to send this across. And then the ETLD field becomes 0 at R9. R9 says, okay, I'll elect myself to be another delegation hub, and I can push up to 5 labels going outbound. And the packet gets to the egress. All right, so in this case, the example here shows a TTL decrement of 1. But if you take a router like R5, for example, he is receiving an ETLD of 5 from R4. R4 is telling him, I can send you 5 labels on a label stack. And R5 goes, I don't think I can read up to 5 labels, get to the IP header and hash and get you a hash. So what I'm going to do is I can only read up to 3. And I'm going to not decrement this by 1. I'm actually going to decrement this by another number, maybe by 2 or 3. And there are very constant algorithms that you can use a number to decide how much to decrement by. But basically, the moment you start decrementing by a higher number, the next delegation hop gets pulled closer to you. So it's no longer R9. If you start decrementing by a larger number, the next delegation hop may be like R8 or R7 because the hops ETLD becomes 0 at a hop much closer to you. So R5 will never receive more labels that it can actually parse. So that's just how it actually works. So when the path message starts on the ingress, gets the egress, the delegation hops have already been auto selected in the network. And so that's just how it actually works. So these delegation hops and labels can actually be shared across different LSPs going across the same path, having the same stack, can actually share these delegation hops and segments. So with backwards compatibility, this isn't obviously the most ideal scenario, but let's say if the ingress routers are upgraded, and they have to be upgraded, transit routers that having old images can actually continue to allocate swap labels like they have been doing today, and ingress can actually have the logic to actually construct the appropriate label stack. So this is just a simple example that shows, just to illustrate the point, that it actually works with certain transit hops not supporting this functionality. Link protection works naturally. So the red and black labels on the links, basically the red labels are used for link protected LSPs across that link, and the black ones are for unprotected LSPs across the link. So if there is a link protected LSP in this scenario, so if R4 to R5 breaks, so typically R4 would have popped a label 301 and would have sent it to R5. If the link goes down, he pops 301, pushes it into a bypass LSP, again lands back on R5. It's the same label that R5 expects, and it works. So just shared a couple of outputs just from illustration point of views, like say a config knob that basically says, hey, this is a pop and forward tunnel. It signals via RSVP a couple of bits that get set there saying, I would like to signal a pop and forward tunnel. The example here shows you a transit router with 64,000 LSPs. And it also shows you a label 300, which is used by unprotected LSPs and is used by 64,000 LSPs at the moment. And that's the entire fib on the box. So it's got one label in there, which is 300. It's shared by all those 64,000 LSPs. This is another example of auto delegation. So here's the top portion actually shows you an ERO that's been computed. This is the path. It's got the RRO that's come back. So it's recorded all the addresses and labels in there. There's like a couple of legends in there called P and D. So P is like these pop labels, like the T link labels, and D is like a delegation hop. So if you look at the rib entry at the ingress, it's actually pushing 3 labels. It gets the packet all the way to the delegation hop, which is the one in the red color, the D. And then if you look at the third hop, you will actually see that the label route on 299.856 actually is yet again pushing 3 more labels to get the packet to the egress. So all this gets set up automatically. So in summary, right, let's just like say, right, traffic engineering, right, of all these years is not a best effort activity, right? Just shoving traffic into the network and believing it will just get there or will get you the SLA that it needed isn't quite right. I mean, there's a lot of planning that goes in via tools, bandwidth and resource management. Want efficient link utilization, bin packing, predict as much as you want predictable network behavior. And if you actually own the traffic that you're sending into the network, you can actually tune a lot of the parameters on the source. But if not, if you're offering a service, you want to do proper planning as such, right, in this network. And RSVP TE as such as a protocol has improved significantly over the years. I mean, in terms of even the scaling signaling extensions that have gone in, have made the protocol to be a lot more stable. It's very less chatty. Refresh times have gone way higher. So that's another data point. And Pop&Go actually offers a pragmatic path towards getting to an eventual controller-driven network, because there's a lot of work that one has to do to get there. And if you don't pay close attention to how that has to be done, it can take a long time for you to get to a proper network, right, with all the parameters that I set up in the beginning of the presentation. So I just want to request your support. It's a draft. It's got accepted in the MPLS working group. There are implementations out there, and so thanks for listening, and open for questions.
All right, thanks. Let's give a warm round of applause for Haresh. Any questions from the group? Very well.
Jabron Krikor with Oracle. Just how does fast reroute work with this? Given you showed node protection with a secondary LSP, how does that actually work in this signaling, or do you still have to run RSVP to get that?
So link protection, the bypass LSPs get set up as normally as they do. The bypass LSPs themselves don't have to be these pop-and-go LSPs because there are very few per router. So if you have primary LSP, standby LSP, so each primary LSP could be a pop-and-go LSP, for example, and the bypasses just get set up in the normal way that they do.
Okay, thank you very much
for link protection. Thank you.
Comment, just on your network. So having worked on maximum seed depth for a number of years, we start with a very simple solution where we just signal number of labels we could push, and then figure out there's some variety in it. Some platforms could push more labels through recirculation. Some platforms can do additional work with performance degraded.
Right.
So I would assume you would want to take ETLD type and provide ability to provide subtypes of it. So one of them is really physical limits, another one, some variations of it. This is what we did in MSD at least.
I see, okay. Actually, the ETLD field attempts to combine a bunch of different things now in terms of how many labels one can push, how many labels one can receive, and so one number tries to manage both of them together.
Anything else? All right, Haresh, thank you again very much for the presentation.